tell us about surprising representations of configurations of class.
Yeah, so thanks so much for the opportunity to speak here. Never been here before, it's very exciting. The work I'll tell you about is in part joined with Melody, Jen, Kristen Bibi, and Claudia Yun, and in another part joined with Louis Eno, who's now a postdoc at the University of Chicago, and I'll mention who is responsible for what as I get to it. And I forgot how to spell surprising halfway through, and I guess it was with a Z, but if this happens, I don't know, I'm not going to be embarrassed about not being a good speller. It's partly not being a native speaker and partly having autocorrect be part of my life. Because, all right. So the surprise part that will show up later in the talk is having starting to think about one problem and then discovering some representations that we know from other parts of math that should be sort of familiar to people here show up, and then towards the end I'll explain why they show up. So something that should be familiar to a lot of people here. So there's hyperplane arrangements in the world of matroids. That's one thing that is interesting to me, and another is tropical geometry and moduli spaces of tropical curves. And those two met up for me in a surprising place, and when they met up, some sparks came out. This is what I want to tell you about today. So the first thing I want to discuss is configuration spaces. And one way to start thinking about configuration spaces is through braid arrangement. Braid arrangement is a hyperplane arrangement that says, thinking concretely inside the complex numbers, and it's the collection of hyperplanes that we might call Hij, which is the vanishing locus, or really the locus of where the ith coordinate and the jth coordinate are equal, and I'm thinking about all the pairs where I is not equal to j. So here's a bunch of hyperplanes inside C to the n. This is the type A n-1 hyperplane arrangement. It's a reflection arrangement. So it has a lot of you can study this arrangement from many perspectives. One perspective is from a combinatorial point of view. The lattice of flats that you get from this arrangement is the partition lattice. It has very interesting poset homology. It's also showing up in homotopy theory in many contexts in physics, and so on. But I see myself as a topologist, and as a topologist, when you have a hyperplane arrangement, maybe one of the first things that you want to do is to give a topological space associated with an arrangement, and that would be take the ambient affine space and remove the hyperplanes. So let's take the complement. And the complement is the space, let's call it M, it's C to the n, where you remove these hyperplanes, which is just, when you think about it, the space it's the space of n tuples of points subject to the condition that no two should be equal. So Zi is not equal to Bj for all I and j. And this is the space that many people would call configuration space of n points in the plane. And as example of a point in this space is I have a bunch of points, and I know which is the first, which is the second, which is the third. And this is an example of a point in this space. And just to sort of be convinced that this is an interesting space, I'll mention that the fundamental group of this space is the pure braid group. And strengths, because if you think of the braid group as a space of loops of these pictures, and if you take a loop that starts and ends with the points being in a row, and instead of playing it as a movie, you play it. This is you put it in 3 dimensions where this is the time direction. And as the points are moving around, we're going to do some kind of braid motion. And the group action here is exactly the concatenation of loops. Right, so these are interesting spaces. And so I started looking at these sort of spaces from the point of view of hyperplane arrangements. But they show up in many other contexts, and you can more generally define if X is any space, you can define the configuration space and points in X to be the space of n tuples of points in your space where no 2 of them should be equal. And when this is a manifold, when X is a manifold, this is a very classical subject in topology and homotopy theory that has contributions by many people. For example, in the 70s, I think, Dusa, McDuff proved that these spaces satisfy homological stability. If your manifold has boundary, then increasing the number of points doesn't change the homology. And this was important for the subject of homological stability in K-theory. But instead of thinking of a manifold, you can take X to be a graph. For example, the graph, here's the graph. It has two vertices and 3 edges. It looks like the letter theta. And you can look at configuration space of some number of points in this graph. So maybe here's 1, here's 2, and 3 might be here. So this is an example of a point in that configuration space. And one reason to care about configuration spaces on graphs is from the point of view of tropical geometry. So I'm sure some people here know a lot more tropical geometry than I do. But one point of view on abstract tropical curves is that they're homotopy equivalent to some metric graphs. And so when you look at this picture, you should think of an algebraic, of a tropical curve of genus 2 with some marked points. And this is actually a relevant perspective following a theorem that with the first set of authors, so Chang, Bibi, myself, and Claudia Jung, that we show that have an SN equivariant isomorphism between, on the one hand, the cohomology of the moduli space of genus 2 curves with n marked points, and let me say a few things about it. So the moduli space of genus 2 curves, ordinarily, if you think of genus 2 algebraic curves with n marked points, these are surfaces of genus 2 with some marked points on them. This could be studied from the point of view of Teichmuller spaces mapping class groups and algebraic geometry in many different ways. But I put the word tropical here because I'm thinking not of algebraic curves, I'm thinking of tropical curves. So tropical curves of genus 2, you can think of as metric graphs that have Betti number 2. So the Betti number of this graph is 2. And they have n marked points on them. So this space is actually topologically a cone. So, and as a cone, it's contractible, so it has no interesting homotopy. type. But if you take the compact support cohomology, then now it has interesting homotopy type. And you can ask, what is the compact support cohomology of this space? And it also has an action of the symmetric group, because these are curves with n mark points. Look at this picture. There's an action of the symmetric group that changes the colors and the points. So this has an SN action. And what we prove is that this interesting representation of the symmetric group is isomorphic SN equivariantly. So let me put a little SN here to the compact support cohomology in 3 degrees less of the configuration space of endpoints on this graph, this theta graph, where you tensor that with some sign representation and look for invariants. Look for invariants under the automorphism group of the graph. And the automorphism group of the graph, so the graph has 2 vertices and 3 edges, so you can swap the 2 vertices, and that would give you an S2 action, or you can permute the 3 edges. That would give you an S3 action. And this sign here, the sign 3, is really the sign representation of the permutation on the edges. So you take this representation of the symmetric group that also has an action of the automorphism group of the graph, because it's going to move the points around, twist it by a certain sign representation, and take invariance. So that's why I got interested in these configuration spaces of graphs, and there is a direct connection to tropical geometry in this way.
But what's the analog in genus 0 and 1?
So I think genus 0, it's tough, because you see there's only one graph here. It's not like, genus 0, you would say it should be trees or something, but then if trees are relevant, then trees should also show up here, but they don't. So there is no analog of this in genus 0 or 1. It's specifically in genus 2 and above. Why
is there a degree shift?
The degree shift? So the degree shift comes in the fact that you have 3 edges. So each edge gives you 1 degree shift. And the sign 3 here is the fact that edges have grading 1. So if you permute things of degree 1, you have graded commutativity. So every edge gives you a shift of 1. You should think of it as E1, E2, E3 as the thing that's showing up here, and each edge has degree 1. So that's the shift. This shift. Oh, 5 edges. More questions?
Compact support cohomology it's the cone, is it the same as the cohomology of the link?
Of the link, yes. Yeah. So this is just the cohomology of the link in 1 degree less.
Gotcha.
So I could have written this as the link of moduli space and then shifted by 2. All right, more questions about this?
Can I take some other genus too instead of theta?
No. Yeah.
So it's only that one.
It's only this one. Yes, exactly. But there's good reason for this. So the moduli space of tropical curves is built from graphs of genus 2, and so some of the stable graphs of genus 2. So there's one that looks like this. There's one that looks like that. There's one that looks like this. And you can also collapse edges and get vertex weights. And I don't know how much people think about this here. But the thing that's special about the theta that lets you eliminate these is that these have a bridge. These have a vertex that you can cut. If you remove this vertex, it separates the graph. So that's why they don't count. And this one doesn't. Everything counts. Like there is no vertex you can remove and separate the graph. So that's why this is the only one that shows up. This is part of the work of Chan, Galatius, and Payne that show that the locus of everything with a cut vertex is contractible in the link. So really, you only need this one graph. Okay, and that's why in genus 1 or genus 0, in genus 0, everything always separates, and in genus 1, there's not enough curves to look at to see that. So there is no analog of that in lower genus. Yeah.
What about higher genera, where I don't eliminate all the graphs with the bridge there?
That's where I want to go.
Okay.
Yeah. More questions about that before I do? Yeah, so natural question, obviously, this is genus 2 curves, and there's one graph showing up. If you want to think about higher genus. So genus 3 curves, when you start eliminating all the redundant graphs, you're not left with one graph, you're left with, so you need to consider 4 graphs. And they have a little structure to them, so you have the complete graph, you have the graph that we call soda can. Both of them have 4 vertices. Then you have, if you collapse one edge, get this graph that I think we called goggles. This looks like, pair of goggles. And then if you collapse the edge at the bottom, you just get 2 edges. And these are the only graphs of genus 3 that don't have separating vertex. But you still have 4 of them. And you need to take every one of them, and for each one, compute the compact support cohomology of its configuration space. For each one, take some invariants under the automorphism group of the graph, then build a complex out of them. And that would compute, this is something also that we proved, that would compute the genus 3, tropical moduli space. But looking at this, a natural problem or reaction that we have is that we need to understand what are these representations of that support cohomology of endpoints on a graph that on the one hand has an action of the symmetric group. That action is going to translate equivariantly to the moduli space side. But on the other hand, it has an action of the automorphism group, the graph. And these actions commute. So if you relabel the points, and then do something to the graph, that you can do it in the opposite order. So these 2 actions do commute. They already commute at the space level. And we want to understand both of these actions at the same time. So these are both finite groups. I'm thinking rational cohomology here, so I didn't say, but this is rational. So I forgot to mention that. So this is a rational vector space with 2 actions of a finite group. So it decomposes into irreducibles. And what do I mean by understanding this? So give me either the character or the irreducible decomposition. Or any way you have of understanding representations of finite groups. Okay, and if you know that for every graph, then you can start building these complexes. You can put this in a device that we have that gives you the cohomology of the tropical moduli space. Right. But this should be pretty scary if you know anything about configuration spaces, because this space really heavily depends on the homotopy type of on the graph itself. If you have 2 graphs and they're not the same, they're not isomorphic graphs, they're going to have very different configuration spaces that can have different cohomologies in different degrees, different representation of the symmetric group. There's no reason to assume that there's any connection between different graphs. So this should be hard on its face, and that is that the on end of a graph depends on the graph in a very serious way. So each one of these problems is on its face a new problem. You have to calculate a completely different calculation for each graph. And people do study the homotopy type of this space for a tree. And what if the tree has only vertices of degree 3? What if it has some vertices of degree 3 and some vertices of degree 4? So these are very hard problems. Even their fundamental groups are really hard. But fortunately, we're not asking for understanding the homotopy type of the configuration space. We're trying to calculate its compactly supported cohomology. And it turns out that the compactly supported cohomology is pretty uniform. Let me explain.
Here, you only took one part of the action on the right. You only took the invariance. You didn't do.
But there's an SN action still, and this is an SN equivariant isomorphism.
I see. Oh, I see. But on the right hand side, so what I was saying is that you have there's other isotopic components of the group.
Oh yeah, yes, yeah, you're right. You're right. Yes, absolutely. So you're saying I only need to know the invariant.
Well, I'm saying here you only did the invariance.
Right, and in any situation, I only need the invariance. I only ever need the invariance of this. Right, so this complex that I'm building, I'm going to take the anamorphism group of the graph, the invariant part of the anamorphism group. Once after you twist by the sign on the edges. So okay. So actually, in a sense, it's not the trivial action on this, it's the trivial action after this twist. So it's the isotypic component that acts with the sign. Yeah, I think you know what I'm saying.
But with the sign, does that ought theta change the sign representation?
Yes, so the S3. The S3 part is that it's the sign of the S3 component. So it turns out that because we're looking for compact support cohomology, a miracle happens. And this is a theorem that I proved with Louis. And I'll say this in sort of informally and then give you an example that explains what I mean. So the presentation. That support cohomology of the configuration space doesn't depend on the graph, or is independent. Graph. I'll put this in quotes, because we need to explain what I mean by that. So up there. Okay, so what does it mean for some representation to be independent of a graph, where obviously the graph does enter through this representation, but here's what I mean. So here's an example. Let's look at compact support cohomology of configurations of 4 points, representation of S4 on some graph gamma. And I won't look in every degree, I look specifically in degree 3, the third cohomology of this space. So on the one hand, it has an action of S4, and on the other hand, it has an action of the automorphism group of the graph. And equivariantly, here's a calculation, a complete calculation for what this will be. So it would have a bunch of summands. First, there's a part in which S4 would act on trivially, and that shows up decorated by this representation. The second wedge power of H1 of the graph. So there's a part that S4 acts trivially on, the automorphism group of the graph acts on the first cohomology of the graph, take the second wedge power. That's a summand inside this representation. Then there's another term, that's the standard four-dimensional representation, three-dimensional irreducible representation of S4. And this is showing up with Sin2. And then you have this two-dimensional representation of S4, if you're familiar, corresponding to the partition 2, 2. This is showing up with just a single copy of H1. And lastly, you have a sign representation of S4 showing up Sin3 H1. So the only thing you need to know is how the automorphism group of the graph acts on H1, and this is a complete characterization of the representation. And it doesn't matter what graph you have. This is a uniform presentation for all graphs. So if you know this fact, that feeds into this machine, and you can start running computer calculations, for example. And we do that, then we get the compact support cohomology for genus 3 curves. We have some computer data about that. Okay, so in general, take questions, but I'll just say generally, you have some representation of Sn, censored some representation of GL, some polynomial representation of the general linear group of H is showing up here. You have direct sum over those, and the automorphism group of the graph acts through its homomorphism to the general linear group of H1. So that's the general formula. Now we can take questions.
What is H in terms of
H is the H1 of the graph. Okay.
How explicit is this? Can you tell me what?
So generally I can't, but I'll tell you some of them, and that's the surprising part. So some of them are familiar, but a lot of them are unknown.
Is it algorithmic in principle?
So we have algorithms, they run up to n equals 10, and then they crap out. So it's algorithmic in principle, yes. All right. So fact, that means there's not too many of these. So the cohomology, the compact support cohomology is, in principle, you have one in every degree, and this is specifically in degree 3. But actually, it's not so bad. This is part of my earlier work with Kristen, Melody, and Claudia, that actually the compact support cohomology of a graph. Let's say graph. It's actually not very populated. It's going to be 0 up to degree n minus 1. Then you have something in degree n. Then you have zeros again. So you only have two places where something happens. You only have two cases where you need to calculate anything. And we know the Euler characteristics, so we know the difference of these two, for example. So that's one thing. It's not too many things that we need to calculate. And let's call this fact number one. And now fact number two is some actual calculations that we know. This is again with Louis. And it's the following fact that the nth graph support homology of endpoints on the graph. It contains inside of it two interesting solutions. So first we have all the alternating powers of H1 of the graph show up. And so this is the representation of the automorphism group of the graph. So I need to tell you some SN representation that decorates it. And the representation that shows up is the following. It's the n minus k homology of M0n, the usual ordinary M0n, moduli space of genus zero curves. Genus zero algebraic curves.
So you,
With n mark points. Yeah. So this is an SN representation, and this SN representation is what decorates the alternating powers of the cohomology of the graph.
What is greater than?
Includes. So, and this is the complete characterization of the alternating power. So there are no other factors that have this representation in them. That's not all, but I want to say a few words about this. So this space M0n is actually also a hyperplane complement. You can realize it as configuration space of endpoints in P1, P S of 2C, which is, this group acts three transitively on P1. So if you have endpoints on P1, you can use the group to move the first point to infinity. Then you have n minus 1 points in the ambient plane, and you can use the two transitivity that's left over to put 1 at 0 and 1 at 1. So this is isomorphic to configuration space of n minus 2 points in the complex plane, and this is realized as a hyperplane complement. So again, if you know cohomology of hyperplane complements, you know the cohomology of this space, but you might think that this should have an action of Sn minus 2, but it actually has a much larger action of Sn that sort of mixes up the hyperplane complement structure. So Sn is acting on this. And the representation that shows up here was already calculated in the 90s by Getzel. He gave a formula for the character, among other things. So in principle, we know what this is. At least we have a generating function for the character of this representation. So this is nice and familiar. And I find it surprising that something like genus zero algebraic curves show up in the configuration space of any random graph. It doesn't even matter what graph you have. But that's not all. Any questions about this? So this is part of what shows up. Then there's another part. It's all the symmetric powers of H1. So if this is alternating power and this is symmetric power, there should be some Stein twist to go from here to there. So there should be some sign twist to go from this representation to whatever should go here. So maybe like an evil twin. So does anyone know a sign twist or an evil twin of M0n, the homology of M0n? Okay, so I'll tell you what it is. So this is something called the White House module. That's also the homology of the space of fully grown trees. This is something that in the algebraic combinatorics community, some people know and really study it in parallel to this M0n calculation. And I'll tell you why this is a reasonable analogy by work of Reiner and Early. This representation is actually the 2n minus kth. So this is the kth White House representation. The n minus kth homology of the space of configurations of endpoints on a 3-sphere mod the group SU2. And in analogy with this is configurations of points in a 2-sphere modulo some groups that act on the 2-sphere. Well, in analogy, you take configurations of points in a 3-sphere, a 3-dimensional manifold, with the action of SU2, which is SU2 is topologically is also a 3-sphere, so it acts freely and transitively on the 3-sphere. So it is the case that that the configuration of endpoints here, you can do the same game, take the first point, put it at infinity, and this is the same as configuration, topologically the same as n-1 points in R3. So this is a linear subspace complement. It's not a hyperplane complement. The subspaces are codimension 3. And because this is a 3-manifold, whenever you try to permute copies, you get an extra sign twist because of the orientations. So this is why this is sort of a sign twisted version of that. Questions about this?
What's a fully grown tree?
I couldn't tell you. I never looked at it from that perspective. I only ever thought of it as that. But initially, this was discovered, I think in the 90s by Sarah Whitehouse, and she called it the Robinson space. This is something that's called the Robinson Whitehouse representation. And she called it Robinson space of fully grown trees. I know it has to do with trees. I don't know exactly what's the definition.
How much is left in terms of dimensions?
A lot. So actually, no, so this is huge. I think this is the majority of the representation. I think this is most of it. But this is not all. So there's many things that are not of either of these two forms. But at least these two we know. Because recently, Roberto Pagaria calculated the character of this representation, an analogous formula to Getzler's calculation. So let me put his name here. Pagaria. The character of this White House representation. Yes.
When k equals 1, you've given us h1 twice, so the left hand tensor factors are the same.
And they would be the same. Yeah. Yes, that's right. I guess that's seems surprising, but yeah, I think that's true. I'll think about it. Maybe there's something that this only kicks in from 2 or more, but no, I don't think so. I think they should just be the same.
But in your picture over there, you only had H1 occurring once. Twice.
No, I don't think it occurs twice. I think they just become the same thing.
Or they become.
Yeah. So maybe I should write this is a direct sum, except that the k equals 1 term is the same. So,
N-1.
ah,
Here is N-1.
yeah, okay, so right, so this is Hn of conf n. There's a similar formula with the same representations showing up with a shift for n equals -1. Thank you. So and similar representation for Hn minus 1. Yeah. So the same two representations, but instead of the k matching, it would be off by 1 if you're in n-1, and here it would be off by 2. Something like that. Because this isn't even. This jumps into every step. But it's the same representations, the same set of representations. All right. So like I said, there's in general, there's going to be some representation of Sn, some representation of the general linear group. And these are two representations of the general linear group. But there are many more representations of the general linear group. And so sim k of d and wedge k of d are two representations of GLD. But they're just two of a large family of operations called the Schur functor. And there's one for every partition. So it's a functor because, like the kth wedge power, it takes vector spaces to vector spaces. So V going to wedge kV. And this is a functor. This is linear. So if you have a linear map of spaces, it will induce a linear map on the wedge powers, and this automatically becomes a representation of GLV. But there are many more. And for every partition, let's say lambda 1, that's lambda 2. Let's go up to lambda k. Maybe some of them are 0. And this is a partition of k. For every one of these, what's the last thing I did? Every one of those, you have a representation. For every partition, you have a functor vector to vector. And these are called Schur functors. And with the familiar examples being the Schur functor of a single row with k blocks is the symmetric power. And the Schur functor for a single column with k blocks is the alternating power. But really, you have lots of things in between. You have things that are, take your favorite partition that's not a row or a column, and you have an operation that looks like this. And that really, these S lambda v are all the polynomial representations of GLD. So these are all the representations where the matrix entries of the representation are polynomial in the matrix entries of GLD. So these are a way of getting every single one of them. So now I can tell you the theorem that I worked with Louis. work out. Yes, you see this every day. So the theorem that we actually proved is that there exists representations W lambda of Sn for all lambda, a partition of some number less than n, and these are graded. So here, graded representations such that the compact support assume configuration of endpoints on the graph that is connected and finite. So every finite connected graph, this representation would decompose as a direct sum of all these lambdas of this W lambda. You can actually the symmetric group tensor the Schur functor lambda on H1 of the graph. And that's how the automorphism group of the graph is going to act. So if you want to give me, if you want a complete understanding of these representations that feed into the tropical moduli space calculations, this now becomes a problem of calculate a representation of the symmetric group for each partition. If you know all of those, you know this representation for every graph. And this is once and for all. So these representations have nothing to do with the graph. This is true for all finite connected graphs.
What are the W lambdas in this example?
So, this is W of this is the W of a column with K dots, and this is the W lambda for K in a row. So let me.
What's the grading of W lambda?
So this is graded because this is graded. So this has degree n-1 and degree n. So there are two things here. So there needs to be 2 degrees in W.
It's only two.
Only 2, yes. And we know the early characteristic of those 2. So the question that is left open is every partition we have some representation. We have these n0n representation of Gensler showing up on this side. Have these White House on S3 mod SU2 showing up on this side. But then for each partition, you have something, some way to interpolate between these two sides. So these are two things that people already thought of as somehow related to each other. But now there's like a continuum of representations between them, one for each partition. And we don't know what they are. So that's here phrases the question, right? There's the question, here's the question mark. So what are these? What are these representations that interpolate between these two sides? And we have lots of computer calculations. I guess we can show the show the slide now.
Your proof give these as the homology of some space, but which then you don't know what the.
Well,
I mean, but
they show up as components of the homology.
like M0N for.
No. We don't know that. this is a lot of punctopy for showing you a table of calculations that we've done. So hopefully it's worth it.
Give it a moment.
Okay. It's going to materialize slowly. All right, so you can see on this side the White House representation, on that side the Gessler representation, and all the partitions in the middle. And here's a complete calculation of all the Schur functors that show up in configuration of dimension 9, configuration of 10 points. So you have a representation of S10 on the one side, and these are all the partitions of 10. These are all the Schur functors that show up. So I highlighted in blue all the places where all the things that are not explained by the M0N part or the White House representation part. So what my takeaway from this is that the stuff we already know is the majority of it. So we can explain all the unhighlighted Schur functors. These are the symmetric powers and alternating powers that we know that should be there. But everything in blue is sort of mystery. And some of them occur with high multiplicity. Some occur with 16 times. I think that's the highest one. So 16 times some multiplicity. All right, so we have lots of data. We ran this on computers. We know all these representations up to n equals 10 points. And we don't know, I mean, there are lots of patterns that we can see and guess, and we have a lot of conjectures about what they are, but we don't know what's actually happening. Yeah.
For smaller n, is the blue stuff smaller?
Yes, yeah. So up to n equals 6, there is no blue stuff. So we get a complete understanding from the two representations that we know. But once you go past that, they start showing up. I guess could be a concern that it would overtake, that there would be way more stuff here, but so far that doesn't seem to be the case. Up to 11 points, I think we account for 94% of the representations that show up. But it does go down as the numbers grow. Can we put this away? This is just to show that we've done some calculations. And what I wanted to do is to tell you, first of all, why these calculations are important, just to enumerate a bunch of places where these representations show up. They're not the initial problem. And maybe also mention why these two things. I want to explain where these come from. Like why these configurations in a 2-sphere and a 3-sphere, why they show up for graphs. So I wanted to say those. Should we take a little break or?
Yeah.
So why don't I first tell you a bunch of places where you need to know these calculations, and then we can take a little break. We need the answer for the following parts of mathematics. So when you're doing punctual theoretical homology. Cohomology. So punctual homology in the classical sense is you take an algebra and you do some operation that has to do with the circle, and you get out the punctual homology of A. So this is. But if instead of a circle, you apply it to a graph, so or something with multiple wedges, what you get out is these representations. And this is something that in the world of homotopy theory and functor calculus, it's expected that if you know what these representations are, you can have complete control over the entire polynomial part, the polynomial approximations of of the stable homotopy category, or even unstable. So polynomial part homotopy theory. And these are exactly these representations that show up. So wedges of circles are kinds of graphs. They're finite and connected graphs. I don't insist my graphs be simple, so this is a graph of genus G. And if you know these, then you can, in principle, do a calculation of the homotopy category. That's one thing. Another thing is understanding representations of the group out Fn, the outer automorphism group of the free group, which is automorphism group of the free group mod conjugation. So these are very interesting groups that have very complicated representation theory, but some parts of their representation theory is polynomial representations in the same way that these are polynomial representations of GLV. And it is the case that the polynomial representation, the category of polynomial representations of these groups is completely dominated by these objects. So these are the injective objects in the category of polynomial representation. So interestingly, so out Fn surjects onto the general linear group. And you can take these representations from the general linear group and restrict them to out Fn. And as representations of general linear group, there's no way to make an extension. There's no way to make a short exact sequence that doesn't split. But once you restrict them to here, you can build extensions, non-trivial extensions. And the question is, how big can I make them? What are all possible ways to take these representations and extend them to something indecomposable? And these are all the indecomposables. That's the answer. So these are the polynomial representation of this group. So if you know what these are, you can start doing homological algebra on the category of these representations. And the last thing, maybe I'll put it here if you want to take a break, is the rational homotopy theory. Of the space of string links. So string links are links in a box where you have n strands coming from the left and the right, and then in the middle, you're doing some kind of tangle like that. You have the space of all of these, and there's an SN action that computes the names of the strands. If instead of thinking of knots in 3 dimensions, you think of knots in higher dimensions, the space becomes connected, but it has higher homotopy groups. And if you want to do the calculation of the rational homotopy groups of that space, it's also governed by these. So there are already 4 different reasons to be interested in these calculations, and it's nice that we already know some large part of it, but we don't know. I mean, depending on what your expectation is, this could be a vanishingly small proportion or a substantial proportion of these representations. Okay, so after the break, I want to tell you why these things are showing up. If you're interested, I'll see you here in a few minutes. Well, I'll tell you why this happens and at least why these representations are showing up. And this is the story. Okay, so the fact is that the decomposition that's given here is part of a larger structure and is maybe I'll say it as an incomplete sentence, the decomposition is a star, where star is this, holds not only for graphs, but actually, so it satisfies two properties. First, that it's not just something that applies for the automorphism group of the graph, it's actually a functor. So the decomposition is natural, meaning functorial maps and continuous maps of graph. Any gamma 1 mapping to gamma 2 would induce a map on this side and would induce a map on this side. And this decomposition is up to some associated graded is natural in every map. So in particular, when you have an automorphism of the graph, it's going to act on here, but actually it's defined much more broadly. And this is where compact support cohomology is really important. So if I just give you a map of spaces, there's no reason to expect for the map of spaces to induce a map on configuration spaces. So if you have an injection, if X injects into Y, then the configuration space of X would inject in the configuration space of Y. These are n distinct points in X are going to go to n distinct points of Y. But if I give you just a random map, let's say a surjection, if I give you n distinct points in X, they're most likely not going to become distinct points in the image. There's no reason to expect that. But it turns out, and this is something that somehow people haven't been thinking about before work, and now it sort of seems that everybody knows it all of a sudden, that when you work with compact support cohomology, there is no problem in defining these maps on compact support cohomology. And the reason is that for a compact space, compact support cohomology of the configuration space of endpoints on X are the same thing as if you take endpoints, if you take just endpoints on X and just say, I want points on the diagonal, on the fat diagonal, let's say X, I don't know how to call it, the diagonal, the ijth diagonal, hij. I could call it before. This relative cohomology is the same as the compact support cohomology of the configuration space. And this is homotopy invariant, and this is homotopy invariant, the natural. So there's no reason to be worried if you have a map of spaces that isn't an inclusion. You can still define it on this side, so obviously on this side as well. So that's the first observation, that it's natural in any continuous map, and it's homotopy invariant. So
Is it a dual there? Or, well, sorry.
So I said the configuration spaces themselves are not homotopy invariants. Two different graphs would have very different configuration spaces. But once you pass to compact support cohomology, it becomes a homotopy invariant, because this is, and this is. Both of these are homotopy invariants. Which means that if two graphs have the same genus, then they would have the same compact support cohomology. So only genus of the graph, which is dimension of H1, determines the compact support cohomology of the configuration space. So as opposed to the ordinary cohomology of the configuration space that's very sensitive to the local degrees and everything. That's the first thing, that you sort of realize that this is not an isolated problem for each graph, but it's actually a functor. So this entire picture is an isomorphism of functors. And decomposing a functor into And we're decomposing a functor into components like this. That's the first thing. And the second thing is that this functor decomposition doesn't only apply to graphs, but it actually applies much more broadly. So the decomposition satisfies, well, it's not phrased properly, but let's say holds for all. Next, that's compact in homotopy equivalent to a wedge of spheres. So any space that has the homotopy type of a wedge of spheres, this functor isomorphism would hold. So you can really think of this as a functor that eats compact spaces with the homotopy type of wedges of spheres and spits out this graded vector space. And this is an isomorphism of functors for that. And the spheres don't have to be of the same dimension. And graphs fit in. So if you have a graph, you can collapse a spanning tree. Collapse spanning tree. And get a wedge of G circles. So because graphs have the homotopy type of wedges of spheres, they fit into a much larger framework. And this decomposition is uniform, not just for graphs, but for all of these spaces at once. And this is the beginning of why these weird spaces show up. Because if instead of taking a graph, we take X to be the 3-sphere, you know that on the one hand, you're supposed to get the compact support cohomology of configuration space of endpoints in a 3-sphere, still needs to be expressed as this decomposition. So it needs to be a nice isomorphic to all the partitions of K, W lambda, tensored S lambda of the cohomology of the 3-sphere, and this is reduced cohomology. But this is one-dimensional. And if you think for a second about the wedge power of a one-dimensional space is going to be 0. And the same way, the Schur functor of a one-dimensional space would be 0 unless it's the symmetric power. So only the sin part survives. So this is 0 unless it's sin k, in which case it's one-dimensional. So what you get is an isomorphism of just the sum of all the W of a single row times a one-dimensional space, and you have on the one hand configurations in a 3-sphere, on the other hand a sum of these graded representations, and all we had to do was solve for these individual components. If you know that this is isomorphic to that, solve for W. And that's how you discover these White House modules showing up. And then to get the M0n, maybe you can guess what happens. You take X to be a 2-sphere. And in that case, what happens is sort of interesting. So now the cohomology of the 2-sphere is again just one-dimensional, but now it has a different degree from graphs. So graphs have homology in degree 1. So the way they commute past each other is like an odd dimensional vector space. But this is an even dimensional vector space. So you get a different sign parity. So in this picture, you're going to be swapping between alternating powers and symmetric powers. So you get a similar decomposition that now the configuration space of points in a 2-sphere is isomorphic to all the W's that are a single column. And again, you just solve for individual components and you discover that fact up there. Okay, so that's it. That's what you came back to. give you another hour. Yeah.
When you feed the, you do this calculation with the computer, how do you teach the computer left-hand side?
So we have, the way we get this isomorphism is we have some spectral sequence that computes it. And the individual terms are some Lie representations, tensor, the cohomology of lambda in some way. And this condition that you're a wedge of spheres means that there are no differentials. So we just have this, we have a presentation for this side as a functor in the cohomology of the space. It's some kind, it's if you think of Mobius inversion, so how do you get the configuration space? You start with the n-fold Cartesian power, and then you start removing diagonals. But if you just remove diagonals, you remove things too many times. So you need to do a Mobius inversion, put some things back in, and then remove them the right number of times. And so the combinatorics that's relevant here is the partition lattice. And you end up getting the homology of the partition lattice tensor the homology of this space many times. And the homology of the partition lattice, we know it's the Lie representation. So that's already implemented in Sage, and we can do calculation.
It was actual sequence of Lie.
But there are no differentials.
Or no, I see. So
Yeah.
just some Lie reference.
It's some Lie representation. Yes. Yes, it's some Lie representation decorated by the cohomology of the space.
How do you feed the homology of space?
Well, it's a wedge of spheres, so it's just some n-dimensional space with the GLV action.
And Sage knows how to decompose this.
Yeah. Yeah. It does.
You know how it does that?
I don't. No, I don't. But a lot of things are reduced to, if you have a tensor a representation of one group, tensor representation of another group, you can turn it into just a vector space by looking at the multiplicity space. That's a nice tool that I'm gonna put it here. So if you have some representation, let's say of a symmetric group, and another representation of some other group G, and I want to know what's the part that's standard for N tensor some W for G, and I want to know this W. Then if you just calculate of Sn representations from standard and into V, that's going to be isomorphic to W. So you can do a calculation in the category of one representation where you just eliminate the other. And the spectral sequence is one where you sort of know how to do this very quickly. So you never have to work with the, if you have a representation of S11 that's 700 dimensional, you never have to actually implement it because you just look at the complementary part. Yeah, so we have a lot of these dimension reduction things. So we never have to work with both the SN and the automorphism at the same time. We either focus on one or the other.
Do you explain this calculation somewhere? Or it's
Yeah, we do.
in the paper?
Yes. Yeah, we also we have a web app.
Amazing.
Yeah, it's on GitHub. Yeah.
What about integral homology?
Oh,
Like, is there torsion, an example? Complex word homology configurations.
no,
Is your functor true for integral homology?
I don't know. This is hard, it's hard. So something that's true for, I don't know how deep you want to get into this, but braid group on 4 strands, the simplest configuration space you can think of. Configuration of 4 points in C, hyperplane arrangement, finite, very nicely behaved. If we know the integral cohomology of this, we know there's no torsion, but it actually is not formal. So there is no isomorphism between the cochains and the cohomology over the integers. There is one over the complex numbers, but not over the integers. And that's sort of getting to like we do calculations using some collapse of the spectral sequence. And we know that it collapses because we can pass between the cohomology and the cochains. But in this case, integrally, I really wouldn't know. There's lots of difficulty. It's a way more subtle world integrally than I appreciated at first. I thought, oh, we just know the cohomology and it's torsion free and it's like we just know what it is. But it's really, once you integrate the cup product into it, it gets really subtle.
Do you know it's torsion free for all graphs?
I think so. Oh, well. I don't know that for a fact. No. No, I don't know. I think I would expect so, but I don't actually know. But again, all graphs are the same. You only need to give me the number of loops.
At the end, you had comp n S3. And earlier you had comp n S3 mod SU2.
Right.
Can you talk about where the SU2?
Yeah, so you have a direct sum of graded representations equal 1 graded representation. So you have many contributions here and only one thing here. So when you sort of factor out what comes from where. Like this is not necessarily something everybody needs to see, but so this is because SU2 acts transitively. You have a homeomorphism like this. And this is a 3-sphere. So you get that the cohomology of this side is just the cohomology of this side, but repeated twice. So you have once in its own dimension and once in like 3 dimensions less. So the cohomology of this space appears twice, and then you match these. It's like, oh, each one corresponds to either this part or this part. This is what I mean by solve for the individual components. But it's a little technical. We can talk about that. More questions?
What are some conjectures that you mentioned?
Like the multiplicity of partitions of this form is n choose 3 minus n choose 2. You know, there's some formulas like that some patterns that we spot, but they don't have any meaning to me. It's just some numerical thing. So Louis, the postback of Chicago, he's very good with numbers. He just like sees these huge tables and he says, obviously there's this pattern here, and I still don't really. I couldn't even match his formulas to this thing. I know they're true, but it's beyond me to like see the pattern. And like there is one conjecture that we could sort of prove by induction, which for me is a sign that we don't really understand what's happening. We know it's true, but we don't know why. But then the other is clear.
Okay, let's thank Nir again.